Hey everybody, welcome. Hope you all had a nice weekend. Um, so let's get into it. So the plan for today is to go through some proofs where we need to prove set equality and kind of finish up this worksheet on proofs with sets using direct proof. And then we'll start worksheet 7, which is going to deal with a new proof technique. So far we just have one, which is direct proof. So we'll discuss a second general proof technique called contrapositive proof, and then we can go through some examples of that. That's worksheet 7, and then we'll finish that up on Wednesday. So your homework for this week is up, and that is going to cover mostly just the proofs with sets. So it's not going to cover contrapositive stuff that we get to at the end of class today. But any questions before we get started today? Okay, so one thing I want to just share with you guys is just to be sure that you take a look at this. Is there's a document up on Canvas with proof writing guidelines, and so I think it's good to kind of keep this stuff in mind. Certainly as we move through the semester, it's going to be more and more important to kind of fall in these guidelines. And so just be sure that you give this a look, make sure your proofs are looking like they're following these guidelines. And so in particular, today we're going to do some proofs, or right now we're going to do some proofs with set equality. So something like this, we might actually do this proof. For example, it's nice to indicate to the reader, there's really two proofs involved here that we'll see, like which part of the proof are you doing before you actually do that proof. It just helps the reader follow what you're doing. Okay, so let's take a look at this worksheet 6. And what you guys read about, partly in addition to power sets that we'll get to as well, was proving how do you prove two sets are equal. And so the general proof here is you want to prove that the first set is a subset of the second, and then vice versa. The second set is a subset of the first. And so if that's the case, if all the elements in A are in B, all of the elements are in B are in A, then they must be the same set. And so last time we talked about how to do each of these proofs. So it's really just doubling that up. So there would be two steps to that proof. So first would be to show that this set, we'll call this one A, is contained in B. And remember, those proofs work with, we start with an element in A, and then we want to show that that element has to be in B. So kind of the general outline here would be, okay, I'm going to start with something in the first set, prove that it has to be in the second set. That proves this. Then we move on and prove that if I start with something in set B, that it has to fall into set A. And then therefore we've got one is contained in the other and vice versa. So they must be equal to each other. So here's kind of the general flow of what these proofs look like. And so just some things that are, again, really nice to highlight here, literally, is, just indicating that what we're doing and this stuff down here is nice to just summarize your proof, just to explain to the reader, here's why we know that these two things are equal. And we'll fill in the gaps in a second. But any questions about the kind of general template for these sorts of proofs? Good. So then if we wanted to kind of connect these dots, if I start with something that's in this set over here, right, then these follow pretty similarly to odd even sorts of proofs, at least this one does. Then we can kind of just write out, well, what does that mean? Well, it means that this number a is equal to 2 times some integer plus 1. And then what might be a good thing to do if we want to get down to this point? Any thoughts? Right, so what we need to show is that this number can also be written in the form, I'm just using m here just to use a different number, that it can also be written as 2 times some integer plus 3. So how can I get a plus 3 over here? I only have a plus 1. So if I multiply, so one suggestion was to multiply by 3. And if I do that, then I need to do the same thing to both sides, right? So people are suggesting to add 2. And so if I add 2, and let me just do some scratch work over here since I don't want to include this part in the proof, but I'd like to have this right? Then I would have a plus 3 on that side, but I can't just add a plus 2 on the right side. So that's right. So I need to kind of keep this. I don't want to change the value of a. So I can add 2 and subtract 2 and then just regroup my operations. So if you're kind of thinking about these sorts of things and you're like, okay, what do I need to get here? A 3, I only have a 1. If only I could add 2. As long as you do that operation and undo it at the same time, you haven't violated anything. You haven't changed the value of a. So just again, doing some scratch work over here, we could rewrite this as 2k minus 1 plus 3. And then what can we do? Yeah, and then we can factor out the 2. Thanks. That's right. So we can factor out a 2 from the k and the minus 2. And now, right, if I multiply and distribute this out, we still get 2k plus 1. So we haven't changed the value of a. We've just written it in a different equivalent form, which is the goal here. And so if you want to include all of this scratch work, you certainly can. I think, some of that algebra seems to be pretty self-evident, I think. So what I could say something here would be like, well, this gives a is equal to 2k minus 2 plus 3. And that gives me 2 times k minus 1 plus 3, which is 2 times m plus 3. For this integer m, which is equal to k minus 1. And I don't think we need anything else to go from this sentence over to here, right? So that shows, therefore, that a is in the set 2k plus 3. Any questions? And so just so you know, since I know this question has come up in the past about like, what does it mean to show your work on a proof? Like normally you want to show all of your supporting work, maybe on your math homework. Here, we're looking for clean essays. So if I do some scratch work on the side, I don't need to see that. I would rather see that cleaned up and explained nicely in a sentence. So that's all I would need for the first part of the proof. Any questions? And then this one kind of should follow pretty similarly. From this, we get that b is equal to 2k plus 3 for some k in z. If you don't want to use k because we used it up top, that's fine. It's almost like when we've finished up this part and we come down to this part over here, it's almost like we clear the cache and we can reuse k since we're finished with the top part. And so then what might make sense to do with this 2k plus 3 if I'm hoping to write this as 2k plus 1? It definitely helps to think about these. Yeah, so we want to split that into that 3 into a 2 and a 1. So I definitely hope that you guys, I appreciate the chats, that everyone's kind of thinking about these since, yeah, if I just tell you how to do it, that ruins the fun, right? Yeah, so then we've got 2k plus 3. So then this gives b can be written as 2k plus 2 plus 1, which gives us 2 times k plus 1 plus 1. So we just rewrite b in the appropriate form. And now this integer n is k plus 1. And so that tells us that this number b, this integer b, can be written in the form of 2 times some integer plus 1. So it's in the other set. And that concludes it. Right now we've got one inside of the other. Both ways, they're equal. So that's what these proofs look like. So it's really 2 proofs bottled up in one. Any questions? Okay, so if not, let's consider these. So these are a little bit trickier. Obviously, these sets are a little bit more complicated. So I'm going to kind of break us up into groups to think about these, since I think it will, you guys will get more out of it if you try and work through it together. But let's just kind of set the template for the goal here. And so for a proof like this, again, there's going to be 2 directions that we need to go. So just for a lack of using A and B, since that's in our already in our problem, what we need to do here I don't know how much space we'll need, but we're going to need to prove 2 things. The first set is contained in the second, and the second set is contained in the first. And then for each of these proofs, we start with something on the left, and we want to show that it's in the set on the right. So for example, here we could say, well, let's let X be some element in A union B intersect C. And then we're hoping to show that therefore this element would be in set Q in this case. Whereas this one would look like, well, let's let some other element, we'll say Y, start in here. And we're trying to move in the direction of showing that Y has to be in the set that we call P. So in your groups, what I'd like you to do is kind of think about how you could connect those statements logically. Any questions? So I'd like you guys to start with 7, and if you get through that one, then feel free to go ahead and think about 8. And then we'll move on to power sets and do some proofs with power sets as well before we take a look at contrapositive proof. Okay, if there aren't any questions coming in.
So this is a 2-case proof.
It's not really cases here, in the sense that we were doing cases before, but yeah, it's like there's 2 parts to the proof. Yeah.
Okay.
And it's possible that in this process you might have cases that you need to consider as well. I don't think that's the idea with these, but yeah, it's 2 proofs, and then these proofs could be any proof technique. So far we just have one, so we're going to stick to direct proof. Yeah.
Okay, thank you.
Yep. So let's see. Okay, so we got 3 rooms of okay, welcome back from your breakout rooms. Yeah, so it's a bit harder to do these, right, when you're just kind of left to your own devices. But to be honest, there's no way to do math sometimes without going through some struggle and making mistakes. That's totally part of the process. So if you felt like you were going in circles, you know, I think you might have gotten more out of it actually than just having me tell you how to do it anyway. So let's kind of touch base on these. Maybe we can just give a little push in the right direction on 8, but I'll kind of leave that maybe as an exercise for you guys to practice at home, and I can put up the solution to that one if you want to check that one. But let's take a look at 7. And so here was kind of the template that we set up together. And so we're going to prove 2 directions here, which is, okay, we're going to start with
screen sharing.
Yeah, thank you. Yeah, okay. So, right, so we're gonna start with, you know, X being in this first set P over here. So that means X is in A, union B intersects C. So I'm just gonna kind of narrate what came up in my rooms. And so when we've got a situation here, so this means so I think like a good thing to do with these sometimes is just like, if you're not sure what the next step is, just write out to yourself, like, what does that mean that X is in here? It means it's in there or it's in there. And so here's a situation where cases might be really nice to do this, because we can see that there's 2 possibilities that we really need to consider. When, you know, you've got 2 cases, that's not so bad. I would say if you're starting to think about things and you've got like 8 cases, that might seem a little tricky. So here we can say case 1, let X be in A. Since either that is true or it's not true. So if X is in A, then if you get stuck, you can kind of look ahead to what it is that you're trying to show. In order to show this, right, what we would need to show, just to put some scratch work here, is that X is in A union B, and X is in A union C. I think I'm going to run out of space, so I will come to a new page. now I've got space. So right, in order to show that this is in the set on the right, we need to show that it's in both A union B and it's also in A union C. But if X is in A, we get that right away. So that's what we're hoping to show down here, right? So that's a bit of an easier case. Then we can think about a second case. And you want to make sure that your cases exhaust all of the possibilities. So that's it, right? There's no overlap, and that takes care of all the possibilities of what X could do. So if we've got that X is not in A, but we've assumed from the get-go that X is in A union B intersect C, and that tells us that it has to be in the other set, B intersect C. So that tells me that X is in B and X is in C. And so then we can say if X is in B, then it's in A union B, that's this part. If X is in C, let me kind of clean it up there. So those would be the two cases, essentially how they could work out. And this might give you some idea of like how much detail do you need. And so with these sets, you really don't want to make the reader make the logical jump themselves. So, you know, to go from a line like this to say that X is in B intersects C, and then to jump right down to this, I think would be a bit much. You kind of need to justify that, okay, why, if it's in B and C, why does that justify that it has to be in both A union C and in A union B? There's not too much you need to say. There's one sentence, but I do think that sentence in between is really necessary to join those two. Any questions? Okay, and so then that's only half of it, right? So we use some cases to prove that direction, and now we go in the other direction. So let's assume we start with something in the second set. And when we've got an and in there, that's nice. So then this tells me two things. That it has to be in here and that it has to be in there. And I think we can then consider the same two cases, right? So if y is in both of those things, then one case could be that y is in A. That's a really short one. That's pretty direct right there. I don't think there's much justification that we need. If it's in one of the sets, then it's going to be in one or the other. Case 2 might be a little bit slightly more to justify there, but the case 2 could be if y is not in A, that would tell us that if y is not in A and it's in here, then it's got to be in B, and it's also in here, so it's got to be in C. Well, I think maybe here it's good to say in between. What we just proved is that it's in the intersection of B and C. Any questions about those two cases? Did anybody do it really differently from the way we've got it here? Anything you guys want to run by me that might have come up in your room? And then kind of the last thing to add here, would be putting a line similar to this, just saying, okay, since we've shown the first set is a subset of the second and vice versa, now we know they're equal. Where instead of these sets 2k plus 1, 2k plus 3, we're now referencing these sets over here, P and Q. Okay, if there aren't questions, in 8, this is what's called De Morgan's Law, or there's 2 De Morgan's Law. This is one of them. So this is asking us to prove this. And again, there would be 2 directions here, which is A kind of union B complement. And that means the complement of A union B. And there's a second direction, which would be, I messed that up. That should be intersection. And certainly you can draw some Venn diagrams here. That's something we haven't done yet, drawing pictures. You could draw some pictures to try and get a sense of what's going on here. But just drawing a picture without justifying what's going on in the picture wouldn't be enough. But if we wanted to think about this one, then we would say, let some element x be in here. And then we kind of just explain what that means. Right? And that would tell me that if x is in the complement of A union B, it can't be in A union B. And so if x is not in A union B, then we know it can't be in either one of those things, right? Or else it would be in the union. That would be one direction there, right? So if x is in the complement of the union, that means it's not in the union. that means it's not in either of those sets. That means it's in the complement of both of those sets. That's the justification there. Okay, so I'll leave the second part of this, which is this part of the proof, for you guys to practice. But any questions before we kind of look at power sets? Okay, so these were the sorts of questions that you had on the reading quiz, and so looking, or at least you had a question on the reading quiz about that. So, excuse me, I think it seemed to go okay, but just to be sure here, if we're taking a look at the power set of A, what you'd want to do, it's going to be the set containing all of the subsets of A. So first of all, right, the intersection is a subset of A. And then kind of a good way to systematically write these out might be, let me first write in all of the what we call singletons, all of this. So we start with the set that has no elements. Then we go on to the set that have one element. Then we can go on and list all of the sets that have two elements. And then the set itself would be a subset of it. So just one thing to note is that we're always going to have the empty set in there, and we're always going to have the entire set in there and everything in between. Okay, so taking a look at the empty set, if we were to look at the power set of the empty set, right, then this set contains nothing. So the empty set is going to be, again, be a subset of everything. And you kind of think about starting with the empty set and then working your way up to the set that you started with. And in this case, we've already reached that point, right? This is the only subset of the empty set. So the power set here is the set containing the empty set. And then this one, again, if you're kind of thinking about how to list these power sets, you can start with the empty set, end with the entire set, and then think about, okay, what would the singletons that are in this set be? So it would be the set containing this thing, and then it would be the set containing the set containing the empty set. So we have this singleton, and then we have the singleton over here. So we're kind of recreating what we did with this one up here. Just now, instead of having numbers, we have sets, are elements of this set. So our elements of this power set are going to be sets containing sets, like this. I think we just listed all of them. Any questions on these ideas, power sets?
Why is that last one? Wait. Okay, never mind. I think I get it.
Yeah, so there's just to kind of label these out, since there's a lot of set notation going on here. This is one element of the power set. That's the second one. That's a third one, and that's the fourth one. And there should be, so all of these things, these are the four elements of that power set. Okay, so let's give this a shot here, doing this one of these proofs. Maybe we'll take part of this power set proof in 10. So we want to prove set inclusion, and let me bring this to a clear page. So we'd like to prove this. I don't think I didn't put any set proofs on your homework for power sets, but you will see that on the next homework assignment. So I think, up to what we've said so far, you guys are good to go for the homework. This is actually, you have some questions about power sets, but not proofs with power sets. So if I want to prove set inclusion this way, now we're going to take an element in the power set. If it's not clear, we typically use like capital letters for sets, right? And lowercase letters for elements in the set. And so since we're dealing with power sets, the elements in the power set are sets themselves. So what we're hoping to show is that any subset of A intersect B, right, should be a subset of A and should be a subset of B. So just to kind of write out in words what all of this notation is saying, if X is in the power set of A intersect B, then what that means is this is a subset of A intersect B, right? And really what we just wrote out here is just definition of power set. What does it mean for an element to be in the power set? And so if X is a subset of the intersection of A and B, then that means I guess, let me be careful here. Just to kind of write on the side these justifications, that first step going from our assumption to X is a subset of A intersect B, right? That's definition of what it means to be a power set. And kind of going from here, whoops. From this sentence over here down to this sentence over here, this is like definition of subset. Right, that means any element in X has to be in A intersect B. I think we're pretty good to go from this point. And this sentence I get by definition of intersection of sets. What does it mean to be in A intersect B? And then just highlighting that sentence, if X is in the set X, that implies that it also has to be in the set A. That's not what I wanted to say, sorry. Didn't want the power set there. Right, that's, again, we're kind of using definition of subset. So really, like, all we're referring to in this proof is these various definitions that we had for set operations. So since X being in the set X implies that it has to be in A, we know that set X is a subset of A. And thus, that means that it has to be an element of the power set of A. And now we can kind of wrap this up with a really nice trick in proofs, right? If the proof for showing that X is in the power set of B is pretty similar, then we don't need to go through like all of the details again, but we can kind of just say, similarly, since X in set X implies X is in set B, we know X is a subset of B, and thus X is an element of the power set of B. And now we've shown that this set X that we started with in the power set of A union B, we've now shown that it's an element of the power set of A and the power set of B. So it's in the union of those two power sets. Or excuse me, the intersection of those two power sets. So that's just one direction, and then we need to prove the other way, which I'll kind of leave us on that cliffhanger there. So for the video that you guys are going to watch for next class is going to just kind of introduce this notion of what proof by contrapositive is. And then we'll spend all class on Wednesday practicing contrapositive proofs. So I will put up solutions to these problems over here, but I'm not planning to go through them together in class. So I would recommend that you guys try them without looking at the solutions. Check out the solutions, and if you do have questions, just let me know about them. It doesn't mean I'm not going to answer your questions. I'm just planning to kind of move on to the next topic on Wednesday. Okay, well, thanks everyone. Yeah, have a nice afternoon. If you got some questions, feel free to stop by office hours. Otherwise, we'll see you guys on Wednesday.